this short-term course. So just very briefly, this is a series of courses being started by the Ministry of Human Resource Development, Government of India, for the last 2 years. And the idea was to collaborate with the expertise overseas and to invite the experts for a series of lectures under 1 week and 2 week courses where the external expert can deliver 20 to 30 lectures over a particular topic. And for that purpose, the ministry has invited the proposals from the various institutions, and pupil in collaboration with the external expert framed the proposal, submitted to the ministry, and it was evaluated through a series of steps. And throughout India, up to now, about 1,400 such courses have been approved, and out of which about 1,100 courses have been successfully run in various institutions. So our university being in the list of university with potential for excellence, and we were lucky to submit these proposals. And in the university, about 16 to 17 such proposals were submitted, and this is the 14th such course which we are going to run today. And our university in the Department of Physics, Chemistry, in Architecture, Food Technology, various courses were sanctioned under this program. So for the last maybe I think 1.5 or 2 years, I am in touch with the external expert we have today, Professor R.C.F. Jones from the Loughborough University. And same proposal was submitted to the ministry and ultimately it got approved. And I'm happy to announce that we are going to start that course today. And for that purpose, I must put into record my sincere thanks to the Ministry of Human Resource Development for the funding and the university for providing all the infrastructure. And not taking much time, as per our schedule, we have to start our course, 2 or 3 lectures we have to finish today. So I request Professor Geeta Hundal to kindly introduce the speaker, and then we will formally start with the course. Thank you.
Thank you, Dr. Palvinder. Good morning. I feel privileged and very happy to bring to you Professor Raymond C.F. Jones, who has traveled from UK up till here to be with you and interact with you. I would like to introduce him to you. In fact, it's a very, very long, introduction because he has got so many things to his credit. So I would like to speak about a few of them. Professor Raymond C.F. Jones is presently Emeritus Professor of Organic and Biological Chemistry, Loughborough University, UK. He has been teaching organic chemistry to graduates, postgraduates, and PhD students for about 42 years, covering all topics within organic chemistry, including synthetic methods, heterocyclic chemistry, and biological chemistry. He has also been active in research for over 40 years, publishing to date 133 papers in international high-impact journals, plus 14 review articles and 3 book chapters or edited volumes. He has given 68 invited and plenary conference lectures and delivered 99 invited research seminars at universities and 35 such seminars at industry locations. His research can be described as organic synthesis in heterocycles and heteroatom chemistry. Principal research themes are total synthesis and methodology aimed at key structural units of naturally occurring molecules, and synthetic molecules designed to have biological properties. His current research emphases are asymmetric synthesis involving heterocyclic templates as control elements, dipolar cycloadditions, modified biomolecules involving peptide mimetics unusual amino acids, example, amidine amino acids in siderophores, and heterocyclic amino acids as peptide nucleic acid building blocks. This research and teaching equips him perfectly for teaching the course proposed herein. As far as his academic journey is concerned, he did his PhD from Cambridge in 1973. Then he got his ICI postdoctoral fellowship in Zurich, Switzerland between 1973 and 74. Then he joined as a lecturer in University of Nottingham in 1974 to 1992. He became a senior lecturer in 1992 up till 1995. Then he became an open university professor of organic chemistry and head of the chemistry between 1995 and 1999. He has been a visiting research professor in Open University between 2000 and 2004. Then he joined Loughborough University as professor of organic and biological chemistry between 2000 to 2016. Then he became a director of studies for chemistry between 2013 and 2016. And currently, as I said earlier, he is Emeritus Professor of Organic and Biological Chemistry in Loughborough University. His other experiences and professional memberships are, a few of them I'll be reading. He is a Fellow of Royal Society of Chemistry, where he was elected in 1980. Then he member of RSC since 1970. Then he was elected as Chartered Scientist in 2004. Sir William Evans Fellowship he got in University of Otago, New Zealand in 2000. He has acted as external examiner for BSc, MChem degrees at 17 universities in UK and West Indies. He has been external examiner for approximately 115 PhD, MSc, MPhil theses at 45 plus institutions in UK, Ireland, and internationally. He has been chairing the chemistry department in UK between 2001 and 2003. He is a member of Engineering and Science Research Council, a peer review college between 1997 and 2015. And to our interest, he is a member of editorial board of Tetrahedron Letter and Archivoc, and he is on the reviewers panel for Chemcom, JAX, JChems, Journal Chemical Society Perkin, Journal Heterocyclic Chemistry, Journal Organic Chemistry, Organic Biomolecular Chemistry, Tetrahedron, Tetrahedron Letters, SYNLET, Synthesis Communication, European Journal of Organic Chemistry, and of course, Archivoc. Among the honors he earned, a few of them, he has been elected president of RSC Organic Division between 2013 and 16. He was elected president between 2012 and 13, and is the immediate past president between 2016 and 17. Then he was elected member and trustee of RSC Council between 2007 and 2011. RSC Audit Committee 2009 and 2011, and member high-level steering group of chemistry in the Center project. He has been chairing the heterocyclic and synthesis group of Perkin Division RSC between 2002 and 2004, and secretary cum treasurer between 1992 and 1996. He has innumerable, research papers as a contribution to this science, which if I start reading, it will be 1 hour gone from his series of lecture which he's going to deliver. So I think I should not be saying more because he is in front of you. You are going to listen to him and you are going to see how lucky we are to have him here. So welcome, Professor Johns, once again. So I hand over the mic to Dr. Pulunga.
So thank you, Professor Geeta, for nice words of introduction. So may I request Professor Jones to come over and take charge of the dais. And one announcement that I would like to make in the beginning is that for the next 5 days, Professor Jones is available throughout the day, and he's also staying in the hostel even after the lectures from here. You can approach if you want to have any sort of interaction with him. So besides this series of lectures, if you have any other problem regarding the organic chemistry, you are free to discuss. Professor Jones, please.
I can't guarantee to solve all your problems. Okay, well, thank you very much for the very kind welcome. I appreciate that. I didn't know I'd done so many things. I'm not quite sure I had the time. And also thank you to Professor Singh for inviting me to help him put in an application for this series of lectures. Some of those PhD evaluations that were mentioned have been done for Professor Singh's students. That was the reason I very first came here. So this is my second trip to GNDU and Amritsar, and I'm very pleased to be back. He would tell you I've been to India many times, about 20 visits. I love India as a country, so I'm very pleased to have another opportunity to come back and connect India and chemistry and myself, so that's good. So I thought what I would begin with is to tell you something about why we put the proposal together in the way that we did, because organic chemistries and synthetic organic chemistry is a very big subject, so we had to select some parts of it to make this course. So I hope, need to tell you here as students of chemistry that, of course, organic chemistry molecules are key to lots and lots of different types of functional molecules. I've just put there pharmaceuticals, agrochemicals, new materials, and of course, the molecules of life, of biochemistry. So we need to be able to make new molecules and new structural types for all sorts of applications and for advances in healthcare and so on. So the idea of developing new synthetic methods is an ongoing goal for chemists and will remain so for as long as I can imagine. But when you look at synthetic methods, most of organic synthesis and organic mechanism relies on reactions of electron-rich species, which we call nucleophiles, nucleus-loving species, with electron-deficient partners, that is, molecules that are deficient in electron and are seeking them from somewhere else, to form new carbon-carbon bonds by things that I will call polar, or not quite ionic, but polar processes. However, there are some bond-forming processes that don't fall conveniently into that category of nucleophile meets electrophile. Whoops, too far. So we decided that that would be the subject of this course this week, and I've picked out, find the right button, I've picked out some things that don't fit into the electrophile, nucleophile category. One of these would be, so there are 3 topics that we will deal with during this week. Electron rearrangements with frontier molecular orbital control that I'll describe in the next 2 days, what are known as pericyclic reactions. The second topic will be reactive intermediates, so benzene or arynes in general, carbenes and radicals that don't fit neatly into the electrophile nucleophile category. And finally, something which has been very strongly developed in the last 20 or so years, and that is organometallic reagents, coupling reactions, metathesis and so on, which depend on catalytic cycles where conventional nucleophile-electrophile interactions don't mean so much. So this course is designed to look at those 3 areas. So this is the structure of it. There will be altogether 13 lectures in 3 groups. At the end of each group of lectures, I'm proposing a tutorial, or you might call that a workshop, where we look at some problems, and I hope that will be interactive with you students sitting in the audience. And I believe I'm obliged to give you a test at the end of the week. So don't think of doing too much on Friday afternoon. Okay, so that's the course structure. The course timetable will look something like this. Today we are, I hope, Monday the 19th, although I'm still a bit jet lagged, but I think that's where we are. So we will do the first 4 lectures on pericyclic reactions today, finish that group of 5 tomorrow, and then have a tutorial session. That'll be the morning. In the afternoon, I think another lecture beginning the reactive intermediates group. That'll be continued on, concluded on Wednesday with a tutorial as well to follow. Thursday and Friday we'll deal with the organometallic reagents. There'll be a tutorial to finish, and then finally a test. I decided not to call it examination because I think test looks a little bit less threatening than examination. And then I believe Professor Singh wishes that we distribute certificates on Saturday morning. I believe that's correct. Okay, so that's the overall structure of the course. I think that's the end of that group of slides. So now I go to the other one, which is to begin talking about pericyclic reactions. So to break that down a little bit further, this is how I plan to divide it. So this first lecture or so will look at introduction, which probably will take a little bit longer than I planned. But anyway, introduction to pericyclic reactions, so what that term means, pericyclic reaction types, and something about the molecular orbital way of looking at that, because it doesn't fit neatly into electrophile nucleophile, but we can start explaining it with molecular orbital treatments and the FMO, frontier molecular orbital concept. Then the second session this morning will be about 4+2 cycloadditions, focusing on the Diels-Alder reaction and features of that. Then some 4+2 cycloadditions this afternoon, the 1,3 dipolar cycloaddition, and as was mentioned in the introduction, that's something that's been quite close to my research interests in the last decade or so. Excuse me, that shouldn't happen. Then we'll look at some 2+2 photocycloadditions and electrocyclic reactions. I'll explain what terms like electrocyclic mean in just a moment. And then finishing this group by looking at sigmatropic rearrangements, and in particular what are known as 3,3 sigmatropic rearrangements. And there are a couple of named reactions and the variants of those within that group. So that's how this group of lectures will work out. I've put in here some additional sources of material. So there's a book called Pericyclic Reactions, one of the Oxford Chemistry Primer series by one of my former tutors, Professor Ian Fleming. There's the textbook by Claydon, Greaves and Warren, at least in those 3 authors in its latest edition. There was an extra author in the earlier ones. And then there are some other sources here. I think I should say that please don't make notes for this. I believe our idea is that we will email copies of these slides are PDF documents, so we'll circulate those to students on the course during the week. Ideally, well, we'll begin later today, I think. Okay, so the first lecture then, which is where we are now, Introduction to Pericyclic, so this is a repeat of what was said earlier, introduction, reaction types, and a bit about the molecular orbital treatment. Okay, so what do we mean by, or why do we have this type of separate classification, if you like? So what ionic or polar reactions, electrophile nucleophile reactions, may or may not have an intermediate, but they certainly have species that are either charged, electron rich, that means Nu- means a generalized nucleophile, or they have partially charged species like the carbon in the middle of this iodoalkane, which is electrophilic, partially positively charged. So these are two reactions that you learn quite early in organic chemistry: nucleophilic substitution, unimolecular and bimolecular, one of which is stepwise and has a defined intermediate, a carbocation, and one of which, the SN2, is concerted, has no intermediate, but can still be understood in terms of polar interactions. And we are very used, I hope, to, in ionic reactions, using curly arrows as our cartoon to identify where the electrons have come from, where they're going, and which bonds have been made and broken. And because we have partial positive and negative charges, we can identify a direction of electron flow. Radical reactions, which will come up later on, don't quite fit so neatly into that, not so single electron species, not so conveniently into partially positive or positive, partially negative or negative reacting centers. So this would be the majority of our organic synthetic reactions will be dealing with electrophile, nucleophile. But then the pericyclic reactions become a third distinct class, where we have, this is a definition by Woodward and Hofmann in 1969, that's Professor R.B. Woodward, that's Roald Hofmann below. Reactions in which all first order changes in bonding relationships take place in concert, so concerted, on a closed curve. So there is no, there are no intermediates that you could identify. Reactions have cyclic transition states. That's where the pericyclic terminology comes in. All bond forming and bond breaking takes place in a concerted manner without any intermediates. So we'll have a transition state with a cyclic array of interacting orbitals and a reorganization of sigma and pi bonds within this cyclic array of shifting electrons in a transition state. These were originally called no mechanism reactions because they couldn't be explained exactly why they're in. That's exactly the reason why they're in this course, because they couldn't be explained by standard nucleophile, electrophile mechanisms that were developed about halfway through the 20th century to try and explain most of our reactions. So here's a couple of classic examples: a Diels-Alder reaction, where the colored bonds are the new ones that have been made. Yes, I've drawn some curly arrows, but I could just as well have drawn those. I've drawn them going round in a clockwise direction, but try drawing them in the anti-clockwise direction. It works just as well. So there's no reason to think about a directionality of electron flow, which there would be in an electrophile-nucleophile reaction. Here is another one. This is actually a sigmatropic shift. I'll say more about those definitions in a moment. But again, you could draw the electron flow whichever way you like, which is what this bullet point is saying. So here we're using curly arrows just really as a way of showing which bonds are being made and broken rather than the direction of flow of electrons. Or you may be wondering who this, so if that's Woodward, that's Hofmann, this is Fukui, who developed a lot of the frontier molecular orbital stuff that I will come on to a little bit later on. So we've got this class of reactions where we can't use partial positives or positives, partial negatives or negatives in terms of charges to kind of understand what's going on. So we need a little bit more. We need to have some kind of orbital treatment. So what are the definitions within that group? So cycloadditions, I use that terminology already, I think, in my synopsis of what we're going to do. Two components come together to form a new ring and two new sigma bonds. So two new sigma bonds to form a ring. So, okay, that Diels-Alder reaction I had on the previous slide would fit that. Two new sigma bonds. Of course, the two new sigma bonds are coming by the loss of two pi bonds in this case. Here's a 1,3 dipolar cycloaddition. Again, two new sigma bonds with loss of some pi bonding. There are cheletropic reactions. We won't say too much about that because they're not so useful in synthesis. are a subclass of cycloadditions, and it's two sigma bonds being made or broken to the same atom. And here I'm showing a breakdown of a ring by losing a sigma bond here and here to produce a small fragment, carbon monoxide in this case. And what's driving this in the ring breaking rather than ring forming reaction is clearly the stability of the benzene system. So cycloadditions, the next major class is electrocyclic reactions. These are unimolecular reactions, so that not two components like in cycloaddition, but one component, characterized by the formation of a ring from an open chain conjugated system with a sigma bond forming across the ends of that chain. So here would have hexatriene going to cyclohexadiene, and this is the new bond here in color. You could imagine the same thing happening with a butadiene going to a cyclobutene. In fact, that one goes in reverse because of the relief of ring strain. So actually that makes another general point, that pericyclic reactions, you must always consider them as potentially reversible, and here it's going the opposite way to ring forming, it's going to ring opening because of relief of ring strain. But the same principle, an open chain conjugated system in on one side of the transformation, on the other side a ring system with a new sigma bond in it. So cycloadditions, electrocyclic reactions, that leaves one, I hope, if it'll go, yeah, one major class to look at, and that's sigmatropic rearrangements. So this is again a unimolecular process, or type of process, an isomerization involving formally no change between sigma and pi bonds, but a sigma bond moving from one place in a system to another. So here is a 3-3 sigmatropic shift. So the colored bond here ends up here, and I've shown the curly arrows. Again, you could draw them in the opposite direction, as with all pericyclic reactions. I hope you can just about see the numbers here. If you start at the numbering from the two ends of the bond that's going to break, and number until you reach the two atoms that are going to be joined in the new bond, then that's a 3, that's 1, 2, 3, 1, 2, 3, between the two ends of the breaking bond and the two ends of the forming bond. So that's why it's called a 3-3 sigmatropic rearrangement, sometimes 3-3 sigmatropic shift. And there are some examples here, a cope rearrangement, which is an all-carbon system, an oxygen in the backbone is a Claisen rearrangement, and so on. You can get hydrogen shifts this way as well, and I'll come in more detail to these when we get to the later lectures in this group. There's some other things at the bottom here which I will skip over for the moment. So cycloadditions, electrocyclic reactions, and sigmatropic rearrangements. Cycloadditions forming two new sigma bonds and sacrificing some pi bonds to do it. Electrocyclic reactions forming one new sigma bond and therefore sacrificing only one pi bond to do it. And sigmatropic rearrangements where we don't change any bonds, we just move them from one place to another. Why do we bother? Why do we need a theory to understand these? Well, what we need to understand is why this one, a diene plus an alkene, will work, whereas this one, which is an alkene plus an alkene, under heating conditions won't work. We need to understand, in this case, the ring opening of a cyclobutene, why we get one E double bond and one Z double bond in the product. Why, when we close this E triene, do we end up with a cyclohexadiene with the two methyl groups on the same side? That's a stereospecific reaction. And the same thing here. Why does this 1,5 shift work, where thermally whereas a 1,7 shift doesn't work thermally, and so on. So there are some things about the molecular frameworks and the stereochemistry that means we do need some more specific understanding of the mechanism. Before we can do that, we need to think about how you can draw molecular orbitals of conjugated systems. So let's say we take a p orbital, which is what's going to make up our conjugated pi systems, and we have two of them in an alkene. Then of course we have two combinations, the bonding and the anti-bonding combination, and in ethene, or a simple alkene, we put all our electrons in here because we only have two, sorry, not all our electrons, all our pi electrons in here. If you go to an allyl system, you will have 3. If you go to a butadiene system, you'll have 4 combinations of those p orbitals to make pi systems. So here's butadiene. Here is all the p orbitals in phase, continuous overlap. Here is where there is one node between adjacent p orbitals, and that looks a little bit like the 2 isolated pi bonds as we conventionally with lines draw a diene. Then we have 2 anti-bonding combinations. We've added, instead of 1 node between p orbitals here, we've added another one. So we've got 2 nodes and then 3 nodes, so that's no overlaps at all. But these are anti-bonding orbitals and are not normally occupied. And then you can extend this through 5 p orbitals in line through to hexatriene and so on. So there is a continuous way of building up these to find all the pi-type energy levels. So if we start, and the key point here is that you end up with the same number of energy levels as p orbitals, or orbitals, but in this case p orbitals you start with. So a hexatriene, you might draw it as in one structure, but it has 3 bonding pi orbitals and 3 anti-bonding pi orbitals, which are not occupied in normal circumstances. So I won't dwell on that, but that's where some of the pictures that we'll show in later slides will come from. Now again, I don't want to dwell on this, but in these systems, the contribution from each orbital at each center is not the same. So here is hexatriene, and it looks, the way I've drawn this picture, as if all of these p orbitals are the same size. In other words, as if all of their contributions to the overall molecular orbital are identical. Well, they're not. I'm not going to go into how this is all worked out, but for example here, you can see that the 2 terminal orbitals, p contributions, are not anywhere near as much as, for example, the one at the 2 at the center. So these 2 here. So although we commonly draw these to make all the p orbitals look the same for convenience, you should remember that behind that there will often be a differential in terms of their contributions to the molecular orbitals we're talking about. And that's the only reason I put that slide there, not to say how it's worked out, but just to show that it is possible to determine the different contributions of all the orbitals to the molecular orbital of the molecule. But there is a sort of easy way of remembering how to put together some of the key molecular orbitals. The highest occupied molecular orbital, HOMO for short, or lowest unoccupied molecular orbital. So the easy one there is the highest occupied molecular orbital, the HOMO of, by neutral I mean uncharged polyenes, is easy to draw because you pretend that it looks like the isolated double bonds, as if there's no overlap. So here is octatetraene, and the highest occupied molecular orbital is just a pair, then a node, then another pair of overlapping p orbitals, then another node, then another pair, and so on. And that is as if it was 4 isolated, independent pi bonds. Now there is, of course, some overlap between the pi bonds, but that's the way of easily, without having to remember them, to easily constructing the highest occupied of the pi orbitals. If you want to do the same trick with the lowest unoccupied LUMO for uncharged polyenes, then you put an isolated p orbital at one end and an isolated p orbital at the other end, and then pair up the ones in between. So this is a nice, easy cartoon way of remembering which ones, or how to draw those two. And the HOMO and LUMO are going to be important when we come to frontier molecular orbital treatment of pericyclic reactions. And that's why I've identified these at this stage. HOMO and LUMO are termed the frontier orbitals, because HOMO is the top one with any electrons in, and the LUMO is the bottom one without any electrons in. So they are the frontier between occupied and unoccupied systems. Now, the way these, I'm going to go fairly rapidly through the next bit because I think it's more complicated than it needs to be, but the original treatments of pericyclic reactions were using correlation diagrams, and with these criteria that during a pericyclic reaction, the orbitals of the starting material are converted into the orbitals of the product smoothly. So that means you need to imagine how they can do that conversion without anything over complex happening. And it meant if you assigned symmetry of the orbitals with respect to symmetry operations in the molecule, the idea was that you had to conserve orbital symmetry going from starting material to product. So a terminology that was used, I guess, back in the 1950s, was the conservation of orbital. Hopefully the technology is still all right. That was just me catching my foot in it, I think. And so the earliest treatments used so-called correlation diagrams. So I'll just whiz through this because I'm not going to use this way of doing it in future. So you drew the bare bones of a reaction by drawing the curly arrows. You identified the orbitals you're in. You imagine them coming together so that the geometry wasn't crazy of the two approaching each other. You identified any symmetry elements that were maintained. So in this case, a sigma symmetry plane being retained in this prototype Diels order reaction. You could rank the orbitals by energy. So this is trying to rank all the orbitals involved. Construct a diagram connecting orbitals of the starting materials with those closest in energy of the same symmetry. So here's a symmetric antibonding orbital connected to another one there, whereas, because that's the closest it can find, there's an antisymmetric to antisymmetric correlation, etc. And yes, there's nothing wrong with that. That theory worked until something more easily handled by simple-minded people like me was developed. But you can imagine doing that for every reaction you're trying to do. It becomes complicated. So these full orbital correlation diagrams, there's nothing wrong with them, but personally, I can't remember them. They're too complicated for me. So other ideas came along, which we'll get to in a moment. But something we did need that was also an idea that was also developed at that time, was and this is about the geometry of approach of components to each other, was there a suprafacial or an interfacial interaction going on? So suprafacial is where bond formation occurs at each end of a system on the same face. So if you've got a pi system, if a bond is forming on the top side, as I've drawn it at one end, suprafacial would have it forming on the top side at the other end as well. Whereas interfacial would mean you're joining one end at the top and the other end at the bottom. Of course, it could be both at the bottom and the other way around in the interfacial, but same side or same face of the system, opposite face. When I say face, because pi systems are essentially planar. You can do the same thing for sigma bonds. Suprafacial would be where the two components in the or two bits of the sigma bond are being on the same side are being used to form new bonds. These curly blue lines are just meant to mean where the new bond is forming from. Interfacial will be where you take, for in a CH bond, here's the sort of H component of the orbital, and here's the back end of the sp3 hybrid orbital that the carbon is contributing. So that would be interfacial. So this kind of definition was needed for a classification, a generation of rules to go with those correlation diagrams. And what Woodward and Hofmann did was took correlation diagrams and distilled it down into simple rules for predicting which pericyclic reactions would be allowed. In other words, which ones would go and which ones wouldn't go. Like I showed earlier on, there were some 4+2 cycloadditions would work thermally, 2+2s wouldn't work thermally. Why? So what they stated, the Woodward-Hofmann rules, can be stated in this way. Ground state pericyclic reaction is symmetry allowed, in other words allowed, when the total number of 4q plus 2, so that would be 2, 6, 10 electrons, and 4 multiples of 4 electrons, Q and R is kind of random choices of letters really, so that would be 0, 4, 8, 12 electrons and so on. So if the total number of 4q plus 2 suprafacial and 4r interfacial components was odd, then that would be thermally allowed. In other words, going from the ground state, so just putting in energy thermally. If it was photochemically allowed, in other words, going from the first electronically excited state, then they would be allowed if 4q plus 2 suprafacial and 4r interfacial components added up to an even number of components. Well, okay, this is less complicated than correlation diagrams, but it derives from correlation diagrams. But even this, I think, is more complicated than is necessary. And there is a sequence. I'll just do it for the Diels-Alder reaction to show how to apply these rules. Draw a curly arrow mechanism, identify the components. Well, we know in a Diels-Alder reaction that's going to be a diene and a dienophile, or a 4-pi and a 2-pi component. Draw a convincing 3D orbital diagram to show that overlap. Label the components as super or interfacial, then add up according to, and see which of these two groups it falls into. So just to show how that can be applied in the Diels-Alder reaction here. So there's our curly arrow mechanism. Identifying the components, that's easy. The 2 pi bonds here and the pi bond in the alkene, the diene and the dienophile. Convincing 3D orbital diagram with a plausible way of approaching. Here's, okay, a diene and an alkene, 2 planar species approaching flat to flat. That seems reasonable. it doesn't seem to be geometrically tricky. And of course, if you do that, then it's logical to think that the two bonds are forming from the bottoms. If you draw the diene above the alkene, then the new sigma bonds are forming from the bottom here to the top there, bottom here to the top there. In other words, suprafacial on the same face in each of the two components. So this is a 4 system, so it falls into the 4R group. This is a 2 system, so it falls into the 4Q plus 2, where Q is 0. So we have in the 4Q plus 2 suprafacials, we have 1 here. In the 4R systems, 4R anterofacial, we have 0, because this 4R system, where R is 1, is a suprafacial approach. So we only have 1 of those components. That's an odd number. That is thermally allowed. Well, that's the result we want, because we know the Diels order reaction works thermally. You could do it the other way up and so on, but you get the same result, however you try and do it. So that shows in outline how you would apply the so-called Woodward Hofmann rules to pericyclic, or to a 1 pericyclic reaction. I've done it again there for a 2 plus 2, but I'm not going to go into that. So let's think about alternative theories. Full correlation diagrams are too complex for easy use. So for lab-based synthetic organic chemists like me, well, not that I've done much in the lab since I was much, much younger, but that's how I started out. People like yourselves. So then Woodward and Hofmann distilled that down into rules, reported that in 1969. They were awarded the Nobel Prize in 1981. Well, Hofmann was actually. Woodward had passed away by then, and you can't be awarded a Nobel Prize posthumously. But effectively, the Hofmann acknowledges that it was joint work that won him the prize. 1981 Nobel Prize was shared. It was shared with Fukui, because by then he had developed a much simpler way of looking at these processes for everyday use by everyday synthetic organic chemists, called frontier orbital or frontier molecular orbital approach. He first started developing that a long time ago in 1952, but then took it onwards from the Woodward and Hofmann rules and had a share in the Nobel Prize in 1981. There is also the Möbius-Huckel aromatic transition state method, and I'm not going to cover that at all in these talks. I'm going to stick with the frontier molecular orbital approach. So, frontier molecular orbitals, these are things you can say about, as two molecules approach each other, 3 major interactions. The occupied orbitals of one repel the occupied orbitals of another. Electron-electron repulsion. Like charges repel. Positive and negative charges, if there are any, either attract if they're opposite charges or repel if they're the same charge. But we're not really talking about charges in most cases for pericyclic reactions, but here's the key one. The occupied orbitals of each interact with the unoccupied of each component interact with the unoccupied orbitals of the other, causing an attraction between the molecules. Where is there the biggest interaction? The highest occupied orbital with the lowest unoccupied orbital, because that's the smallest energy gap. And the interactions of occupied with unoccupied are bigger the smaller the gap between those two. So frontier molecular orbital theory or approach considers the interaction of the HOMO and the LUMO to be of overriding importance. They are the closest in energy in terms of the full empty overlaps, and and that interaction is considered to be the dominant one. Look at it another way. A HOMO orbital is filled, highest occupied. LUMO is empty, lowest unoccupied. When you interact those two together, the electrons that were in the HOMO go into the bonding combination between those two, which is stabilized compared to where they were before, and not into the anti-bonding combination. So for a thermal reaction to happen, where molecules are starting off in their ground states, then you want filled orbitals interacting with empty, filled with empty on the two components. And that doesn't work quite the same way for photochemical reactions, where we've got some promoted electrons, and that's what's shown in the bottom of this, but I won't deal with that for the moment. We'll come back to that a couple of lectures' time. So just to say again, in bigger letters this time, why frontier orbitals? Frontier molecular orbital approach considers the interaction of the HOMO and the LUMO to be of overriding importance. Said on the last slide. Why? HOMO-HOMO and other filled-filled interactions, no energy gain. In fact, a repulsion, so certainly no energy gain, so why would they interact? It's not going anywhere. LUMO and other empty-empty interactions, no electrons, so no energetic contribution to the reaction. So basically can be ignored from that point of view. The HOMO-LUMO gap is the smallest filled to empty interaction. The smaller the gap, the more stabilization from the positive overlap, the bonding interaction between those two. So that's why the overriding importance, because this is going to be the biggest stabilization you can get. And if you can work out that, and this seems to work, the frontier orbital approach, then it gives an easy way of assessing whether a reaction is going to be allowed or disallowed. I won't say forbidden, because that's not quite right, but have a higher energy barrier. So I like allowed and disallowed, favored and disfavored. So that's why the frontier orbital treatment, I think, is so important. So here's the Diels order reaction. You might wonder why the slides keep changing colour. The ones that are like that, they're the ones I made with the Loughborough University logo. These have been borrowed from other colleagues at other universities with their permission. So the frontier orbital approach, how do we apply it? You have to work out what is the HOMO and what is the LUMO in each of the components, and have a look at how they interact. So you haven't got to do a full correlation diagram, you've just got to look at maximum of two interactions. You could call them correlations, but interactions. So it's very simple to apply to reactions with two obvious components like cycloadditions. It's more tricky to do it in sigmatropic reactions, where you're just moving a bond around. But we'll see how you can make it work, and we'll see how that happens when I come in more detail to sigmatropic reactions. So what do? You draw a curly arrow mechanism, just like you do with any of these. You've got to work out what's going on, what's involved. So, of course, there's a simple prototype Diels order reaction with its curly arrows drawn to show you its two pi bonds on one component interacting with one pi bond on another component. You assign a single HOMO, a single LUMO to the reaction, draw a convincing 3D orbital diagram. Well, okay, we had to do that in the Woodward Hofmann, so that is the same. Check to see if there's constructive overlap, if they're overlapping properly. Okay, let's try that for the Diels order reaction. If we put the HOMO on the diene, it's a conjugated system, so the HOMO looks like two isolated double bonds. Thinking back to that cartoon way of how you draw the HOMO. The LUMO of the dienophile is just the anti-bonding pi orbital, so that's pi star of any old pi bond. So you draw it. You draw a reasonable approach between the two. That's convincing 3D. That's exactly as we drew before. And then you look and you say, and of course, shaded and unshaded on these is arbitrary, but once you've done it, you can see, okay, there's two unshaded lobes, that's a good interaction. Two shaded lobes, same phase of the wave function is what the two shaded lobes means. That looks like a good interaction as well. So it's a constructive or good overlap. Okay? That means the reaction should work. But I arbitrarily put the HOMO on the dyne on the LUMO on the dienophile. What if I'd chosen it the other way round? LUMO on the dyne, well, if you go up to the, if you go one orbital up in butadiene, this is what you get. An odd, a single p orbital at one end, then a pair, then a single one at the other end. That again fits into the cartoon of how to draw these orbitals. The HOMO of an alkene is easy. That's the pi bonding orbital. Draw them, choose your shading and unshading correctly, and there we've got two constructive overlaps. Surprise, surprise, it works. It must do. We know what the result's going to be. So the theory is producing the right result, so it's an acceptable theory for the time being. That's a reminder of how it was with the Woodward Hofmann approach. But I'm going to use this frontier orbital approach from now on. How am I doing? Getting close. Whoops. That might be the last. Okay, so actually I have got through that in the time I hoped. Okay, so this is the background to explaining these orbitals. I'm using here the frontier orbital approach, and I'm using a cycloaddition to illustrate it, and in fact that's what the next session is going to deal with, a little bit more detail for the Diels-Alder reaction, because there are other components about stereochemistry, reactivity, and substituent effects that we need to look at in a little bit more detail to go with this kind of basic picture in this prototype reaction. So that's all for this first session. Thanks very much.
So, would you like to ask anything? Any query?
You feel free to ask questions now, of course, but as Professor Singh said earlier, I'm around, so you can approach me at any time. I think I'm quite a friendly, approachable person, so don't be frightened.
So we have a break for tea for half an hour, and we assemble by 11:30. So tea will be there just outside the store in Coastal. Okay.